Hi, my name is Maxim Stojkovic, and today I'm going to be talking about peer-to-peer energy trading using hardware-in-the-loop simulation. Over the past decade, the adoption of renewables has continued to accelerate, with the Australian average annual growth rate rising from 3.9% to 4.6%. This has led to a growing need for a redesigned electricity market structure that allows prosumers to participate alongside large industrial generators. Additionally, as the penetration of distributed energy resources, or DER, owned by prosumers increases over time, electrical networks may become affected by issues such as overloading and overvoltage as a result of bidirectional power flow in networks. Thus, to address these problems, multiple DER integration approaches have been developed, each having varying levels of network awareness and customer focus. The primary focus of my research was peer-to-peer energy trading, which offers a unique compromise between optimal power flow and home energy management systems, as it can be readily deployed in existing electrical infrastructure and modified to ensure technical feasibility while maintaining high economic efficiency. Peer-to-peer energy networks provide a platform for facilitating the localized trade of electricity, improving social welfare for prosumers by executing trades between retail feed-in and time-of-use tariffs. The peer-to-peer model is also highly extensible, allowing network oversight mechanisms to be integrated, which enforce network constraints and address the aforementioned problems with rising DER penetration. Previous research in peer-to-peer modeling encompasses the analysis of various auction-based order clearing algorithms, as well as the development of mechanisms which prevent trades from violating network constraints. The consensus on peer-to-peer models within literature is that the market structure promotes high economic efficiency while offering great flexibility and autonomy to both market operators and participants. Due to the emerging status of real-time digital simulation technology, previous research on hardware-in-the-loop testing has only covered the integration of simple physical systems such as a single solar panel and basic loads. Additionally, hardware-in-the-loop integration methods outlined in literature were identified to be dependent on specific testbed hardware configurations, with the primary challenges being system stability and accuracy. Thus, my research aims to further the current understanding of hardware-in-the-loop methodologies by proposing a robust integration strategy for steady-state system analysis which maintains stability and accuracy in suboptimal operating conditions. The main objective of my project was to integrate a continuous double-auction peer-to-peer energy trading model into hardware-in-the-loop simulations to assess the feasibility of peer-to-peer networks as a DER integration approach. Within these simulations, a Zero Intelligence Plus algorithm was used to model prosumer bidding strategies, as it is often cited as being comparable to human decision-making in the context of freely competitive markets. The implementation process involved combining a real-time simulated electricity network with physical hardware representing a household prosumer that is actively trading in a peer-to-peer market. To coordinate hardware during simulations, a communications library was written in Python, allowing fine-grained control over individual devices across multiple different communication protocols. To simplify the distribution of the project's codebase, images were created using Docker, an operating system agnostic platform that works as a lightweight virtual machine with all the dependencies needed to run simulations. Additionally, Ansible, a software provisioning tool, was used to automate the deployment of Docker images and execution of simulations across 5 Raspberry Pi computers, each representing a single prosumer within the peer-to-peer network constructed. In addition to streamlining the simulation process, the automation tools developed as part of this project provide a highly scalable foundation for future research, allowing new hardware, more prosumers, and alternative DER integration approaches to be easily incorporated into real-time simulations. As shown in this slide, at the beginning of a 24-hour simulation, prosumers are relatively inactive, before experiencing a sizable increase in active power exports due to solar generation. Towards the end of the simulation, prosumers continue trading electricity to generate additional profit and ensure sufficient power for the next 24-hour cycle. In the main simulation used to collect data, a total of 32 trades were executed between prosumer households, as shown in this star-shaped diagram. The orientation and thickness of arcs represent the direction of power flow and amount of energy exchanged, respectively, during each trade. As expected, Household 4 participated in the most transactions, as it represents a regular consumer household without solar panels or a battery system. It also follows that as households become more self-sufficient, the greater the total compensation received for trading electricity at a competitive rate. Transaction data collected during simulations shows that the majority of social welfare generated through trading is received by the buyer side of the market. This can be attributed to the Zero Intelligence Plus algorithm used for prosumer bidding strategies, as unlike stock markets where foregoing a trade does not result in realized losses, residential consumers are highly inelastic and will always choose to purchase electricity at the lowest price available. The irrational buyer-side behavior shown in the right half of this graph, indicated by a non-zero closing bid price, means that consumers are actively choosing to pay the higher time of use tariff instead of trading with another prosumer, despite the assumption that electricity from both retailers and prosumers is perfectly substitutable. Ultimately, this prevents the price of electricity from rising throughout simulations, resulting in a buyer-favored market, which warrants further research to accurately model rational prosumer decision-making. Testbed data collected shows that during simulations, the hardware configuration used provides a highly accurate representation of expected output values with a median relative error of 5.45%. The median was deemed the most accurate representation of expected error, as relative error exhibited high positive skew for active power set points close to zero. While the model and hardware configuration developed were considered suitable for steady-state network analysis, my research also found that current residential-grade inverter technology is subject to extremely high levels of harmonic distortion, bringing into question whether electrical supply authorities and network operators agree with large-scale DER integration. For example, Part 3.6 of the AS61000 standard specifies guidelines for voltage and current distortion at supply authority points of connection. However, stricter requirements may be enforced based on the existing status of the network. Consequently, further discussion with regulatory bodies and network operators related to power quality considerations will be necessary to mediate DER integration as electrical networks rapidly evolve in response to climate change. Additionally, advancements in residential-grade inverter technology will be critical for large-scale integration, as currently these inverters are designed primarily for self-consumption rather than injecting power back into the grid. To summarize, by developing scalable automation tools for the distribution of a custom peer-to-peer communications library, it was possible to coordinate physical hardware for use in simulations with 5 Raspberry Pi prosumers. Additionally, the data collected proves that with sufficient design planning, a stable and accurate model can be constructed, which overcomes the limitations of residential-grade inverters. To reduce the latency introduced by analog I/O and allow for transient system analysis, a fiber optic link could be used in place of analog systems. However, this is expected to introduce new integration challenges which are not well documented or extensively discussed in literature. To better represent practical field applications, the testbed should also be converted from Ethernet to 4G networking to ensure hardware remains operational when deployed in households. Research into Zero Intelligence Plus modifications or suitable alternatives should be performed to identify more accurate methods for modeling the behavior of inelastic electricity consumers. Lastly, further research, analysis, and discussion related to network operator incentives is necessary when considering the feasibility of DER integration approaches, as poor power quality may compromise the stability of electrical networks while increased competition threatens the bottom line of a naturally monopolistic industry. Overall, it has been an absolute honor to work on this project and learn more about the future of electricity networks. Thank you for watching.